The gravitational potential at a point V is defined as the work done, or rather the negative of the work done per unit mass in shifting the mass from a reference point. This reference point is usually taken as infinity. So we are bringing the mass from infinity or a certain particular reference point to the point under consideration, and as we are moving the mass, what is the work done per unit mass? That particular work is done per unit mass is called as the potential. So formula wise, this will come out to be negative of integration of F dot dr. So this force happens to be the net gravitational force on the mass upon m. Okay, but we know that force upon mass is nothing but the gravitational field. So this is going to be integration of E dot dr. So because of this particular expression, we also get the fact that E happens to be equal to the gradient of V. So it's del V upon del R essentially in radially outward polar coordinates, or this is also called as spherical coordinates, but with a negative sign of course. And E being a vector quantity, we'll have to write R cap over here. And this is the partial derivative. This derivative is the partial derivative. So this particular concept is slightly mathematically intensive without going too much into the depths and details of what a radial gradient is in spherical polar coordinates. I'll just write down this expression and we'll understand this expression more when we solve questions. So E, if Cartesian coordinates are given, then E is going to be equal to minus del V upon del X I cap minus del V upon del Y j cap minus del V upon del Z k cap. Alright, so these are the expressions relating the potential, field and the force. So essentially, physically speaking, potential is the work per unit mass. So it can also be defined as the potential energy per unit mass essentially. So we are talking about unit mass when we talk about gravitational potential. So potential is nothing but the potential energy per unit mass, means from infinity, let us say we are moving some object from infinity, let us say infinity is represented over here, and let us say we have our collection of masses, let's say mass m1, m2, m3, etc. All these masses are creating a gravitational field throughout space, and we move our mass from infinity. So let us say this is the mass that we have over here, and we want to move that particular mass from infinity to a finite location. So this mass we want to move from infinity to a finite location. Let us say we do that, and now the mass disappears from infinity and comes to a finite location over here. Let us say the mass comes over here. Then in such a case, the work done by the net force of gravitation in moving this mass from infinity to over here at a finite distance. So here infinity is taken as the reference point. So the work done will be given as integration of F dot dr. The potential change or the potential at that point essentially is defined as, so here at infinity potential is assumed to be 0. So change in potential is nothing but V at that finite point R. Let us say this point is called at, okay, I'll rather label this point as, let's say P. So V at the point P minus V at infinity is going to be negative of the work done. So positive work, if positive work is being done by the gravitational force, potential decreases. The negative sign comes in as a result of that. So it is minus integration of F dot dr whole divided by m. So this is the change in potential. So potential essentially represents potential energy per unit mass. What is the potential energy? The potential energy is the potential energy associated with the gravitational field. Gravitational force being a conservative force, it conserves mechanical energy. So there is a potential energy that can be defined. The potential energy is defined as du is equal to minus F dot dr. Potential energy is also defined in terms of change, not absolutely. So also because of this, we are going to get minus del u upon del r is equal to F. Just like we got minus del v upon del r cap is equal to E, this particular expression. We could also write force is equal to minus del u upon del r cap. This we can write. Also, in the gradient notation, we can write down. So, let me circle this first. So, it is isolated. Okay. So, in the gradient notation, we can also write down the force F to be equal to minus del u upon del x, which is the partial derivative with respect to x. That means we assume other variables to be constant and only x to be changing. So x is the only variable. Even if the expression contains y, z are to be assumed to be should be assumed to be constants basically. Yeah. So essentially, these two expressions are one and the same. If we divide the force expression with the mass m, we get the potential and field expression. If we divide the force and potential energy expression with mass m, we get the field and potential expression. Okay. So this is the concept of gravitational potential. It is essentially the potential energy per unit mass, which means the work done per unit mass in bringing a mass from an infinitely far away point, which is usually the reference point, to a finite point. So negative of the work done by the gravitational field per unit mass. This is defined as the change in potential. The potential at infinity is assumed to be 0, so the potential over here is going to be Vp. Alright. So because of this, for a point mass, the expression for potential is going to be, so for a point mass, let us say we have a point mass. We'll go to the ring in a moment. We have a point mass. So from infinity, if we are bringing a test mass, then the force dot dr. So this is V at a finite point at, let us say, point P minus V at infinity is negative of integration of force dot dr upon m. So force happens to be Gm m upon r square, and dr happens to be just dr, and force and displacement are in the same direction now. So because of this, we are going to get this to be the case. So after cancelling out m, we'll get integration of dr upon r square, which happens to be r raised to minus 1 upon minus 1. So Gm upon r square integrated dr. So this gives you Gm upon r with a negative sign as the potential of the point P. Alright, so here so basically the expression for potential of a single point mass is minus Gm upon r. This is something to be noted. Now here for the ring, what do we have? For the ring, we have a conglomerate of points. So this is a continuous object, so there are infinitely many points. However, potential being a scalar quantity, we don't need to take any components. So let us say we want to find out the potential at a point which is at a distance of r from the center of the ring. So this distance happens to be r. So we can just find out what is the distance of this particular point from all the points on the edge of the ring. So that distance happens to be under root of r square plus capital R square, capital R being the radius of the ring. So this is the radius of the ring. capital R. So the potential is going to be simply V is equal to minus G dm upon under root of r square plus r square, the integration of this. The only variable is mass, so after integrating this comes out to be minus gm upon r square plus r square, the whole root. So this is the expression for a ring, expression of the potential for a ring. This needs to be remembered by the student for solving questions related to potential. Next, let us move on to a hollow sphere. We note that the field inside the hollow sphere is 0. So potential is not going to change inside the hollow sphere. Inside the hollow sphere, since the field is 0, the potential is going to remain constant. And outside, the potential will simply have the expression that it has for a point mass. So V is going to be equal to minus Gm upon R, where R is going to be greater than equal to capital R. And V is equal to constant, which is minus Gm upon R, the surface value. So this is for R less than R. Potential cannot change suddenly, otherwise the field, which is essentially the gradient of potential, will become infinity, and we don't want the field to become infinity. That's not practically feasible. So potential cannot change suddenly, so it has to be continuous. So the expression, let us say we draw the graph for a hollow sphere. The graph will look like this. So this is the graph of potential versus R. So the graph is going to look like this. So it will be negative Gm upon R. So this value, this particular value happens to be negative Gm upon capital R for points that are inside in the interior region. So in this particular region, in the interior region, and on the surface, the potential happens to be negative Gm upon R. And on the exterior, once we get to the exterior, then we get a graph like this that tapers down to infinity. This is proportional to 1 upon R. So to be exact, the value of this potential is going to be minus Gm upon R. So we are drawing potential as a function of R over here. Alright, so if we move on to a solid sphere, now without derivation I am going to state the expression. So for outside points, the expression obviously remains the same, and also for the surface point. So for outside and surface points, V remains the same. So V is equal to minus Gm upon R when R is greater than equal to capital R. So for inside points, we need to integrate as per the field, which is Gm upon R square into R by R. So I leave that integration to be pursued by the student. I'll just write down the total expression of the potential. So the expression of the potential is going to be given as follows for points inside. So V is going to be equal to minus Gm upon 2R three R square minus R square upon R square. So this can be rewritten as V is equal to minus Gm upon R cube, 2R cube rather, into bracket 3R square minus R square. This is the exact expression. So because of this, we understand that we are at the center. So basically R is the distance from the center and capital R is the radius. So we understand that at the center, the distance from the center is going to be 0. So at the center, the field, the potential on the field, the potential is going to be minus Gm into 3 by 2 R. This is going to be the potential. So this potential is maximum magnitude wise, the potential is maximum at the center, because the gravitational force has done all the work it can do to reach the center. Also, one thing to note is that phi center, the field at the center, happens to be equal to 3 by 2 times the field at the surface, because the field at the surface is going to be given by gm upon capital R minus gm upon capital R. So it's 3 by 2 times v at the surface. Alright. Okay. So this is the exact expression. Now if we were to draw the graph, then we'll have to understand that the graph would be variable, because the expression of the field varies as r varies. So the graph would be something like this, wherein at this particular point, let us say the radius is there. So this is r. We are drawing the graph of potential versus the distance r from the center of the solid sphere. And this particular value happens to be minus 3 by 2 gm upon capital R. So it is maximum at the center at 0 distance, and this particular value happens to be minus gm upon R. So it's maximum in magnitude at the center.